सर
हाँ सर बोला. हाँ सर बोला.
तो अटेंडन्सचा थोडा इश्यू येतोय पार्टिसिपंटला, जरा सॉल्व्ह करावं लागेल आपल्याला.
हो हो हो
ते मध्येच काहीतरी टेलिग्राम वगैरे पाठवतात, ते म्हणलं
हो
की
हो हो.
वी आर बिझी इन द
त्यांना
सेशन. सो
त्यांना मी सांगितलंय, डोंट वरी
बघूया
अबाउट अटेंडन्स, अटेंड द सेशन्स प्रॉपरली, डोंट वरी अबाउट अटेंडन्स. सांगितलं मी कालही.
ओके. सगळे आपले प्राध्यापक मंडळी आहेत ना.
हा आता आपण सुरू करू. उर्पेकर सर जॉईन झालेले. हा.
गुड मॉर्निंग. झाले का?
गुड मॉर्निंग सर.
ऑडिओ बंद आहे त्यांचा.
मला वाटतं यायचे
नाही आले.
ऐकू येते का माझा आवाज?
हो आवाज ऐकू येतोय. हो येतोय सर.
ओके.
गुड मॉर्निंग. गुड मॉर्निंग. उडपीकर सर गुड मॉर्निंग.
गुड मॉर्निंग डॉक्टर सत्ता.
गुड मॉर्निंग.
Then I'll not wear the headset. Thank you.
Speaker, Dr. Udpikar sir, Dr. Vishwas Udpikar sir, which is he is a director of SIVPAPA software, and he has a 37 experience in the research, development, and innovation. I request to Dr. Udpikar sir to start first session, which is based on DSP and DIP application for research and industry, which is a part of signal and image processing. Yes, sir, please, sir.
Yeah, thank you very much, Doctor. So we will start. So first of all, once again, thanks for an opportunity given to me today. I assume that the little summary discussion we had yesterday was in line with the theme of this program. And we discussed a little bit of technologies that are used in signal, image, and video processing. I try to present that more through some examples. And we also looked at maybe some very basic approach-related topics. And I talked about a new sensing technology that's coming up in imaging. So today what I want to do is just focus on a few applications. So these are, I think the purpose of this is to say how relevant the area of signal, image, and video processing is. I think it's quite clear to everyone that vision or audio or host of other sensory signals play a extremely vital role in our life. And any kind of machine processing of these signals is obviously going to bring a lot of benefits to us. So the relevance of this technology is now need not be said again, that it's extremely relevant in today's world. All of us carry a lot of signal processing on us. Everyone carries a cell phone that's probably loaded with signal processing techniques in their pockets. So today I have picked up two sets of applications. Today I want to stick to my time, unlike yesterday. So in 45 minutes time, I'll give you a brief run through this application called GeoLut receiver. This is a satellite communication application and something very interesting, something very important in today's world, and how every step in this is linked to signal processing and what kind of technologies are used to implement an application like this and what benefit it's bringing to us having set this up. And roughly about half the time we'll devote for this, and then we will go to look at image processing applications which are in the industry, the machine vision, where we do industrial automation using cameras, computers, and things like that. And I also want to show you some applications of the time of flight imaging camera we talked about yesterday. Okay, so let's get going. What is this GeoLut receiver? So I hope you are all able to see my slide. Panelists, can you please confirm?
Yes, sir, we can see. No problem.
Okay, yeah. So
your video is not on.
My video is not on. Okay.
Yeah.
You see what? Mm. Oh, I think I have to stop sharing, then turn the video on. Yeah, okay. Sorry, I forgot to switch the video on. Is it coming, or or am I not allowed to?
You're allowed.
Uh, Surprisingly, it says the webcam can't be connected. I don't know. There is something.
There might be a driver issue.
Yeah, no, but it was all working.
We can continue.
Yeah, so I guess it's okay. I mean, there are more interesting things on the slide than my face.
Yeah.
So, let's I think talk about the slides. Yeah. Oh, I need to share again.
You have to share again.
Yes. So you all see it now?
Yeah, it's available.
Yeah. Okay. Yeah. There is an international consortium called COSPAS SARSAT, and this consortium coordinates the search and rescue effort for anybody in some kind of emergency on this planet. And obviously, this is using it's heavily reliant on the satellite segment. And the system works very well, so that any kind of emergency, let us say a maritime emergency or a flight emergency or an expedition emergency, the people who are trapped or are under that kind of emergency can alert the world, and the world around can take suitable action to rescue them. So, for example, if there is a ship and that is, let's say, for some reason met with an accident and is sinking, so what it does is it carries an instrument called a beacon, and this beacon emits a signal at 406 megahertz, as is written here. And this signal goes all the way to satellites in the sky that are specially designed. They have transponders specially designed to listen to this kind of signal. And this satellite acts like a bent pipe, and it just sends the signal back to Earth, only thing at a different frequency. So this is at 406 megahertz. What comes down from the constellation of satellites is something at a different frequency, and that depends on the listening station's capabilities. So India is a member of this COSPAS SARSAT consortium, like many other countries are. But our membership has a little bit of a speciality that you all know. We have several satellites of Indian origin in the sky, and they provide this satellite segment also. Apart from the search and rescue segment on Earth, we also provide support through this segment. So the signal that comes from somebody who's under emergency goes down, comes to the listening station, goes to a receiver, and there is a processor there that understands what the signal is. From this signal, it figures out who's this under emergency, what kind of emergency, and most important, what's the location of this party that's under emergency. And then this message is immediately sent across the world to the rescue teams, the search and rescue teams, and they go and look at the problem and save as many lives as they can, and things like that. And this is something that's working in the background while we talk. And every moment there is something happening, and every moment there is some kind of support being given by systems like this. And we provide, that is the Indian Space Research Organization provides a very important component in the system based on the satellites and ground support. And our satellites that are involved in this system presently are geostationary satellites, which are at such an altitude that their relative position to a point on Earth does not change. So the satellite is always at some known location in the sky. So this height is incredibly large. I think it's several tens of thousands of kilometers. So the signal that goes from the beacon to this height and comes back obviously is not a very strong signal. It's a weak signal. And there could be very large number of parties that are under some kind of emergency at any given point of time. So there has to be like a frequency allocation for every beacon. So the spectrum that's allocated for this job, there could be signals at different frequencies in the spectrum at the same time. And all these weak signals have to be then received, demodulated, decoded, understood, and the action has to be taken. And let's not forget that the most important thing is this action has to be taken as quickly as possible. It doesn't help to provide rescue after several days after the event has happened. It has to happen as early as possible so that large number of lives can be saved. At the end of this little slideshow, I'll show you some examples of search and rescue done through the Indian segment support. Since our geostationary satellites are at such a high altitude, they have a very large coverage area. We almost cover with our satellite tip of South Africa to almost the Australian subcontinent, Australian continent. So yeah, this is a very large area, and a lot of it is on water. So a lot of maritime activities occur, and there is a strong need for this kind of support in this region. To be sure, we are not the only ones who provide this support. Of course, there are French and Americans and Russians and other countries' satellites also providing the support. But there's no competition here. There's only the motive that we save as many lives as possible. So whoever sends the signal to rescue team earliest helps to save very precious lives. And I think at this point would like to say that our system also has sent several such messages to save precious lives. So we'll understand why this is a signal processing application and why it is a complex application, so that I'm really selecting this to tell you about. So for that, let's look at, well, this slide just shows a bunch of beacon products that are available in the market. So somebody who's going on a maritime mission or a flight or an expedition in the mountains can simply buy a beacon like this and carry it with them. Even fishing boats can carry a beacon. In case they get stranded, they can activate the beacon so the rescue people know where they are and they can come and rescue them. So as you can see, not all of them are very large ones. Some of them in fact fit in the pocket. So this clearly tells me that the power I'm going to send up to the sky at 406 megahertz is not a very large power. There's no huge power source here. There's no large battery here. So with this limited power, the 406 megahertz signal, by the time it reaches the satellite, it's weakened considerably. And as I said, it's a bent pipe. So satellite doesn't do any signal processing as such. It only changes its frequency and sends it down. So it can't really improve the signal to noise ratio situation. And then it travels back again so many tens of thousands of kilometers. So it weakens further. This slide just tells you that there are different types of beacons, and those of you who are interested can search this on the net and also see if you are going out on some expedition, what kind of thing you need. This is all in the public domain. Now, let me just, with this little hand sketch, tell you what is the problem and why it is so interesting. So B1 is let's say, a party having beacon 1, and let's say it has activated the beacon because there is some kind of emergency. So what it does actually is it emits a burst of signal, roughly about 520 millisecond duration, and this is repeated every 50 seconds. So it's like it's equivalent of the cry, save me, save me, save me, every 50 seconds, right? And this burst is supposed to carry information about the identity, about the location, and so on, right? Now, this burst, when magnified, and if we had a chance to capture it on an oscilloscope, it's going to look something like this, right? Heavily buried under noise. Actually, I've drawn a much cleaner signal here. In reality, it doesn't look anything like this. It only looks like noise. But the structure of this signal is decided by this organization, COSPAS SARSAT. And what they have done is they have built features into this so that the communication becomes robust. So in 520 milliseconds, the first 160 milliseconds, they only send a carrier signal, right? A carrier signal which carries biphase shift keying modulated signal in the next 360 milliseconds. So this carrier helps for any receiver to get the phase of the carrier. So this is supposed to be the feature so that your local oscillator on the receiver side can lock to it, right? And you will see how in signal processing, eventually this gets used for demodulation of the bits. Now, in this 360 milliseconds, there are two major areas. There is something called frame synchronization. So some of you who are in wireless communication would know that there is always a feature in the packet whose purpose is only to make sure that the communication is happening correctly, right? So it's giving the right fixed pattern information so that the receiver knows the pattern beforehand. And when it sees the pattern, it says, aha, I'm on the right signal. So this modulated frame sync, roughly about 16 bits at 400 bits per second, is the first part. And then there are 144 bits at 400 bits per second, which is information about the party. And this is all phase modulated or phase shift keying modulation technology is used on the signal. So this is roughly how the signal looks. And mind you, this is not the only thing that we are going to encounter in sky. When your antenna looks up in the sky, it is going to look at beacon B2, beacon B3, and God knows if it's a bad day on Earth and many emergencies, it could be even B100. So when the beacons are manufactured and sold, you can't really allocate frequency to every such beacon precisely. So if a fisherman wants to buy a beacon in the local market, you can't say that you are given so and so frequency to work on in that 406 megahertz band. So what is done is the beacons are manufactured with variable frequencies. There's no specific control on that. And the assumption is that people buy these in different geographic areas. So the frequencies would be anyway different. The other thing that can be different is the activation time. So, for example, this B2 has activated himself a bit later than B1. So you can see that the burst of B2 is exclusive or is not overlapping or is not interfering with the burst of B1. So you can either have time division multiplexing between beacons, or you can have frequency division multiplexing. That is, by chance, if B2 is activated exactly at the time as B1, which is extremely difficult or very rare probability, that two different boats in two different regions are activating beacon exactly at the same time. But by chance it happens, then we rely on the fact that they would have different frequencies. So it can be frequency multiplexed as well. So now let's look at the challenge. The challenge is I'm getting the signal. I'm also getting a lot of interference, by the way. Satellite communication is not used only for this. There are a lot of other signals. There's a lot of other terrestrial signals. Industrial areas around my receiver station are emitting interferences. So the spectrum really looks completely cluttered. And from that, we have to see the right signal and get it in as quickly as possible. So first signal processing that happens, we talked a little bit about techniques yesterday, so I'm going to just bring references to that, is that whatever the signal is coming, we keep on finding its Fourier transform, right? And we do it in a small time segment, small enough so that I have the required frequency resolution, and it keeps on scanning this entire thing spectrally. And the moment we see a peak in that 406 megahertz band that we are looking at, we ensure that the peak is coming at least certain number of times, so that 160 milliseconds divided by my F50 period, let's say that number is 5 for the sake of example, then I should see the peak at least 5 times continuously. Then I know that I am onto the beacon. So what I have to do is mark this point in time precisely. Understand that marking something in time is marking something in digital count, because we have an FPGA which is clocking at some clock frequency, and the count of that at that clock frequency defines actually the relative time. So I mark that count, go, and I keep doing this continuously. I mean, I can't. I need parallel processing here, because this the module that's looking at the signal in the sky cannot stop even for 1 millisecond. So it keeps doing that, and it only gives the reference of the time where the likely burst is to another processor element which is running in parallel. So this goes on, and then the processing element takes it over. And what it does is it finds this end of 160 millisecond period from the beginning, and then it knows that next 360 millisecond is my candidate signal. So it gets that, and first 16 bits worth time period, it scans for the known bit period or the bit pattern, and that's called a frame sync. Now to get the bit pattern, you have to do what is called demodulation. And they are getting caught by the antenna. And from this, we have to understand these particular frequency signals that are mentioned here, their first burst time, and the beacon message as decoded in bits. And this is the frequency timetable that I talked about. And this keeps running on the screen, and the process keeps picking the right burst from this. So the 1 to 8, 8 to 15, 16 to 23, and 22 to 30, all of them were caught by the system. And this was one of the important tests. Yeah. So these then we actually turned our attention to real beacons. So this was not a test beacon, but something that was really happening in our region, that is South Africa to Australia. And these also were caught very well. And I think with this, the system passed, and I think it was a kind of a proud moment for everyone that ISRO received a certificate that you are admitted to this consortium to provide the space segment support. Yeah. So I think I'll skip the details of noise and other things, except I just probably like to mention one small thing. We measure the signal strength by carrier to noise ratio. So it's a ratio of carrier power to the average spectral density of noise. And this, as you can see in this plot, we require at least 40 dB hertz kind of C by NO ratio to decode our signal correctly. This C by NO converted to a signal to noise ratio in the bandwidth that is allocated for the signal works out to a negative signal to noise ratio. So it's a very challenging thing. Another interesting challenge we faced is that I think it's probably clear from earlier description that the frequencies get entered in this table. Now let's say I have a beacon, it's emitting some frequency F1. What is the chance that this frequency will drift? So obviously it will drift because the beacon is not a very special piece of equipment. They don't charge lakhs of rupees to sell you a beacon. It will at the most be few tens of thousands. So its frequency can drift. The frequency can also drift on board satellite because the satellite goes behind Earth so that it is in shadow of sun for half the time, and maybe half the time it is directly facing sun. So the temperature on the satellite can change by several hundred degrees centigrade. And with so much temperature change, there is obviously some frequency drift in all the electronics on board. So because of this, we notice that the frequencies that we get for the same beacon, they keep changing. And this was a very interesting fact that came out of this. They could measure what is the drift on the satellite by our instrument. So it was a very interesting fallout from this development. So I'll just now, in the few minutes that are left, I'll talk about a few real distress situations where the system was useful. We actually, our first real interesting application came not in a search and rescue kind of situation, but in a simulated or a kind of a test that ISRO did in 2007. Yeah. So they were doing what is called a space recovery experiment. So you all read in the newspapers that there will be astronauts Indian astronauts going to space. And many different countries follow different ways of recovering something from space. So Americans have this shuttle that lands like an aircraft on a runway, and Russians use a parachute, and then the capsule is dropped. So I think the Indian idea was something similar, that it will be a capsule. I mean, these are all experiments. Nothing is fixed yet, but this experiment would drop a capsule from space. So somewhere here it will be released from the satellite, and then it will fall precisely off the coast of Chennai in Bay of Bengal. And this experiment was done by dropping a dummy capsule, obviously. And how do we know where it is? So the idea was to put a beacon in that, and as soon as it impacts with water, the beacon will activate, and since our system was there, it will give the latitude, longitude, and we can just go and recover the capsule. So this was a really interesting moment, and as you can see, our own beacon, we got decoded. Its location was precisely found. These are the lat longs captured on an Excel sheet, and then the towing party could go there and pull this capsule towards the coast, and then it was driven away to Sriharikota. So in future, maybe this technique will be used for actually bringing astronauts down, and in that case, this receiver is going to play a role there. Then there was another experiment they did where it was dropped in the Andaman Sea, and there also the system immediately captured its lat long. In fact, I was told that it was catching the lat long even when the capsule was falling from the sky. Because the geostationary satellite is so much above, the beacon was activated while it was falling, and even during that period, it was catching the location. A couple of real distress situations. I think there was this huge super cyclone near West Bengal and Orissa coast, 2013. And that time there were many boats that faced problems. There was, I think, this particular one with Chinese and Indonesian sailors that capsized, and their beacon activation was sensed by our system very quickly, and the search and rescue team could go and save their lives. So this Economic Times report says that 17 Chinese and 1 Indonesian were rescued from this capsized boat from this. So this is all the kind of report the system gives. It gives the location, the time, and all those things. Then several other such distress situations like chopper crashes and aircraft crashes and all were reported by this system. There was also a particular incident that was narrated by ISRO to us that some individual boatman from Australia actually strayed away into the waters, and his boat capsized almost 90 miles off the coast, and he activated his beacon, and we in India received the signal first, and the message went from our system to their search and rescue center, and they could save his life. So there was a special note of thanks from their government. So so this is the brief description of the system. I saw some questions coming up like what's inside the receiver and things like that. So maybe I think we could discuss a few of them now. So do one of the coordinators want to ask the questions?
Yeah, we can take it just now also.
Okay.
One of the question is what are the components that are present inside the receiver box?
Okay, so as I said, there is a very high-speed A to D converter in the front. The input signal is 70 megahertz, but the bandwidth around 70 megahertz is limited. See, each beacon is modulating at 400 bits per second. So the bandwidth of each beacon is very small. It's just about a kilohertz or 1.5 kilohertz at the most. So the bandwidth that COSPAS SARSAT has allocated for this application is about 80 kilohertz. So around 70 megahertz, we only have to deal with 80 kilohertz. So some of you might be knowing that there's this technique called sub-Nyquist sampling. So even if the signal is at 70 megahertz, since your bandwidth is only 80 kilohertz, you don't have to really apply Nyquist theorem and sample at 140 megahertz or more. You can actually sample at a lower frequency. So we do that. The AD converter does sub-Nyquist sampling. It's a 16-bit ADC, and then this signal is then down converted to baseband from 70 megahertz. Yesterday, I talked briefly about this down conversion. So what the down conversion does is it first applies a band limiting filter. It's a digital filter, and then it does dropping of samples, and that in signal processing terminology is called decimation. So we decimate. So out of 10 samples, we'll pick only one, then the 11th, then the 21st. And so on. So that would be like dropping the sampling rate by a factor of 10. So this kind of down conversion is done to bring the signal down to baseband. And once it is in baseband, then starts all this business of FFT and the demodulation and all that. So for that, the components used are an FPGA and a DSP. The DSP is a analog devices Tiger Sharp DSP in the system, and the FPGA I believe is a Xilinx FPGA. Yeah.
Mr. Arvind is asking, beacons are manually activated or
Yeah.
automatically activated?
There exist both types. So normally all flights, aircrafts carry beacons which are automatically configured to automatically activate on impact. So in case if there is an unfortunate crash or something like that, they can activate automatically, and they obviously can be activated manually by the pilot or the commander in case there is some other kind of emergency.
Swapnali is asking whether dataset for the beaker will be available for processing for the researchers.
So I told you that we had this problem when we started. So our own simulator. I think it will not be possible to have the receiver data obtained from ISRO. I think for various reasons, it may not be possible to share that. But the COSPAS ARSAT website gives a complete description of how the signal is formed. So if you just visit the website and understand the signal format, it's very easy to write. I'm writing probably MATLAB code to generate the signal.
Vishwas sir.
Yeah.
Pranjal is asking what is the frequency range used in beacon used for SRE?
It was same frequency range. So the beacon that they carried was a standard beacon. So it is emitted at 406 megahertz in that 80 kilohertz bandwidth I just said.
Okay. Next question is from one of our participant. Why it is the capsule is called as dummy capsule?
Oh, because there were no astronauts in it.
Okay. Just to check.
India will probably do that in some years. I think we all are waiting for that, right? An Indian in space in our own, technology.
Yes. Shankar is asking which software is used to analyze the signals.
Yeah, I missed that saying that. So most of this was all coded in C. So this is all embedded coding. So it works out most optimally in C. I touched upon topics like optimizing while you write code for performance, or the topic of response I said yesterday. So it's very critical that the available time, every cycle of the DSP or the clock cycle of the FPGA is used gainfully. So it's mostly done in C. So there are no overheads, and FPGA is coded in VHD.
Okay.
Even the topic of responsiveness is a very important topic here. For whatever reason, if the system faces some kind of problem, see, obviously, you have seen a Windows screen in my presentation, right? So there is a dependence on a host computer with Microsoft Windows and all kinds of things. So it's always possible that there is a system like this that will face an unexpected crash or a problem, But you can't be stopping the reception. So there is a fail-safe responsiveness feature here. That is something like that's happened. The system actually restarts automatically.
Yes. So next question is from Sumed. He's asking what is the approx cost of a beacon?
Yeah, the beacon you can buy I think few thousand rupees also, very low power beacons, to fairly complex, those that turn on impact and would have higher power for reliable detection. They could go in lakhs of rupees also.
Okay. Next question is from Anju. What is the difference between signal and image processing? She is asking.
Okay. We talked about this yesterday, so I'm happy to answer again. Signal processing, like I just told you, the application that is signal processing. The waveform I had drawn was some signal as a function of time. So it's a one-dimensional signal, right? Of t, let us say. Whereas in image processing, image per se has two dimensions. There are two independent variables, x and y, and the spatial coordinates. So image processing is a multi-dimensional problem, ideally two or typically two. And as against in video, you have x, y, and t. You also have time. And we discussed yesterday that time gets represented by sequence number of a frame. So you have an image frame, next image frame, next image frame, and so on.
Okay, sir. Next question is from Sonia. How are messages exactly exchanged from Earth to space?
Well, the beacon is a small antenna. I think that photograph probably was not very clearly seen. Each of those beacons had a little bit like a sticking telescope, a small antenna coming out. It's like a small stick coming out. And then that emits the power. So you can again see, I mean, it's a good question that this antenna cannot be directional. The beacon can be lying on its back or on the front, or it can be standing vertical and so on. So unfortunately, this 406 megahertz power is emitted in all directions.
Yes.
Actually, ideally, it should be emitted only towards the satellite, but we don't know where the satellite is. In a moving boat, we cannot be aiming at the satellite all the time. So this is a big problem, that the power that is available, most of it is wasted because it is sent in directions that are not useful. So this antenna sends it to the sky in all directions. One of them happens to be the direction towards the satellite, and the satellite picks it up.
Yes.
Okay.
So the next question is from Mohini. What is the reason that crash in Bermuda Triangle can't be traced?
I don't know, ma'am.
So,
Really don't know. Sorry. I think it's of interest to many people, but
yes.
it's of interest to me too.
So mysterious question is there.
So
next question
we
is,
move on to the.
for one more we can take.
Okay.
How the polarization of antenna affects the signal received?
Yeah, so I think this particular project or this particular implementation does not use a polarized antenna. So naturally, I think polarization plays a role. And most important aspects of polarization are used to sort of make the communication reliable in presence of atmospheric effects, turbulences, and so on. So there are other SATCOM systems that do use specifically polarized signals. See, again here, the beacon being a very simple device, you can't really generate a polarized signal from it.
Okay, we'll take next questions at the end of the session.
Yeah, so I am going to be very brief in my next session. So I'm really going to pick up the vision system examples. Not all of them are possible in a short time. So here goes. Yeah. So we talked yesterday about the 3D camera. Now what you see here are boxes put on the conveyor belt. And the 3D imaging camera is looking at this arrangement from the top. And in Windows here, you see different outputs from the 3D camera, especially this one here is the distance image, right? So as these boxes go on the conveyor belt, we are measuring their volume automatically. So let me run the video again, or it's running again. So this is box one. And when it passes under the camera, you will see that 4,657 centimeter cube. The small box is 682 centimeter cube. The slightly bigger one is 1288 centimeter cube, and so on. So this is an application where you can measure volume of an object by looking at it. See, volume measurement is a challenge in industry. Things like weight can be measured by a strain gauge or a load cell suitably mounted. But volume is really depends on the shape. And because this time of flight camera we saw yesterday is giving us distance to every pixel from the camera, we actually get the 3D profile of the object. And from that 3D profile, it's possible to find its volume. So this particular application is done for all these logistics companies that are sending boxes to your homes every day through home delivery. And you can imagine their handling centers. They probably handle several lakhs of boxes every day. and then they need to be arranged in size wise. They have to be sort of sorted and all that. So it is not possible to do it manually. So these automatic systems use time of flight cameras to actually know the height, width, and length, find the volume, and based on that classify. Incidentally, the camera gives pixel distance at every point. So this can be done for irregular shaped object also. So it could be a bag of cement and you could find its volume as it goes under the camera. So this is one example of the time of flight imaging system. I'm going to show you another example, and this is in robotics. And this is a demonstrator application. We made a robot, a simple robot, a kind of toy robot that's used in college student projects. And what's put on this is a time of flight imaging camera. And what this robot can do is it can understand its environment in 3D. So one of the things, simplest things we made it understand is presence of a wall, right? A wall is a flat surface. And that's why this robot is called a wall follower or a wall F robot, right? So it uses this camera and the robotic platform. In fact, it also was a technology demonstrator for a framework called Robot Operating System. Yesterday we talked about frameworks. So the field of robotics uses ROS as a framework. So we built that into the hardware here. And then the camera signal goes into that network. And what happens is actually a interesting feature that without any training, the robot knows that the wall is to its left, and it's presently programmed. It's presently programmed to follow the wall at, I think, 1 foot distance. So it precisely maintains that distance. And interestingly, it can understand when it hits the corners. So the dynamics of this, dynamics of this robot are not really very fancy. So that's why it is, I'm going to just forward a little bit. Yeah. So it takes time to turn because its dynamics are not very good. Now here, it will come to a convex corner. It's not a concave corner. So it knows that it has to turn left, and then it turns left. So this it has achieved without any training. Such demos you might have seen with a black line put on the floor, and then the robot follows that black line. But here, there's no such thing that you can just say follow the walls and put it in any room. It will just go around following the walls. And of course, this is not a greatly useful application, but it tells you that a lot of things can be done with this in industrial automation when things are to move from one place to another. A camera like this can give a precise position feedback. So there's another example, again related to robotics, and this is gesture control. So this again is a technology demonstration. So we used a simpler time of flight camera here, the small one, and we made it recognize hand signs of this kind. Stop, keep moving, turn left, turn right, come back. And these hand signs we passed on to a robot to sort of follow them. So in this video, you will see that this is the camera and the operator is giving commands to the robot, turn left. It started turning left. And it keeps going because both signs were there. It keeps going, stops, comes back. And this is where the fact that I was telling you yesterday, that the segmentation of the hand is done on the basis of distance of every pixel on the hand from this camera. So it cannot miss. It cannot get confused by the color of the hand or color behind the hand and things like that. There's no chance that the segmentation will fail. It's looking at all pixels which are within certain distance from the camera. So it automatically filters out things which are beyond that. And I think this makes the whole process of gesture recognition very stable or very robust. Okay, so I will show one more example of this 3D camera system, and this is in vehicle counting. So this is in our own office, and we have a gate, and cars and scooters keep moving in and out. So it's a 3D camera output here. So 2 bikes went out. That's why the out has become 2. And the segmentation again is done on the basis of the 3D image. So we can actually find the exact volume of the object that's going out. So the security guard went out, that's why person became 1. Car went out, the out car became 1. Two-wheeler has come inside, it has become, bikes in has become 1. So this very precise classification, completely independent of ambient lighting conditions, shadow, color of the object, and so on, is possible. So another car is going out along with the pedestrian. So the pedestrian also increased by 1, and a bike went out. So this is the advantage of the system. Now you see same performance at night, where the normal camera doesn't see anything. This is a normal camera output, but the 3D camera still sees the same image, right? Where the gray level here is proportional to the distance. Far away objects have higher gray levels, closer objects have lower gray levels. So car has gone out, so it just said car out, right? So this is the advantage of this time of flight imaging technology. Yeah. Okay, so let's look at a few other applications now. I'm going to select some. Yeah, so let's select this. We talked about tracking yesterday. I showed you one example of tracking. This is another example. This is using this DSP box, and it's got a fixed camera to cover this entire area of surveillance, and its output controls a pan tilt zoom camera to focus on a moving target. So you see this car has come in, and the zoom camera is automatically zooming on it. There's no human intervention there. It found out the size, it decided the zoom factor, it found the location, and the zoom camera was directed on that car. Now, subsequently, you will see a lot of interesting movements happen. This man is walking in, the camera starts tracking this man automatically. So these kind of video analytics are very useful in surveillance. And I mentioned yesterday to you that this famous Lucas Canaday technique for image segmentation, that technique is used here in real time. Every frame is passing through that kind of segmentation. And the output is then used to drive the pan tilt zoom camera so that it starts tracking the moving objects in the scene completely automatically. Now with this, you can do a lot of things. You can make a virtual fence, and in this virtual fence, all the, this lady walked into the fence, so it marked the location where she went into the fence, and an alert can be sent to a guard or whatever. This system is configured not to alert somebody going out of the fence. So when she walked out, there was no alert. Now this two-wheeler will go into the fenced area, virtually fenced area. So it gets marked, the location gets marked, and his alert is sent. So all these kind of analytics, they are called virtual fence, virtual tripwire, and so on. They are implemented in this system. So these were the security related applications. Let me show you one or two core industrial applications. Okay, very interesting. You have seen such flares in refineries and chemical factories and so on. Now this requires a vision monitoring so that there's no black smoke coming out of it. So this is a clear bad example where there is a lot of black smoke coming out, right? So this is a flare monitoring system that there's a camera pointed at the flare, and 24/7 it is looking at the color of the flare. And the moment it sees a color that is, incompatible or is out of the accepted range, then it sends an alarm, and then the refinery's process can be corrected. So there are many countries, especially in the Middle East, where pollution laws are very strict. So if this kind of black smoke comes out, this can be a invitation for a huge punishment. So the companies are very interested so that they get an alert right when something like this happens. So this is one industrial example. This is an interesting one. We talked yesterday about different kinds of sensing technology. So our company also works in X-ray imaging. So this is an example of mithai getting inspected under X-ray. So these are little burfi pieces, and then if they have any kind of contamination by chance, this can happen. Maybe a burr from a machine part, or some piece of wood, or piece of glass, or something like that may remain inside, and it can't be seen visually. So inside a chocolate or a piece of mithai, or pre-packaged food like noodles and namkeens and so on, they may have something like this. And these can't be inspected by visual methods, so you need to pass them under X-ray. So we have this system which automatically look for such contamination and flag that pack. Recently, our team has done something for raw food items like potatoes. So companies that process large amount of potatoes, like those that make wafers and things like that, they have to sort potatoes, and the bad ones have to be removed. So they have their way of calling defects, and some of the defects are visual outside and some are internal, and the internal ones can be hollow hearts or cracks and things like that. So again, they pass through X-ray, and this is our screen of our X-ray system that is looking for internal defects also. And it's like this one has an internal defect, so it is failed. The second from the top has failed. And then with a rejector mechanism, this is thrown out, and this entire thing is moving on a high-speed conveyor belt. Okay, I'll show you one more example, and then we'll probably stop. We have a lot of print inspect solutions. See, printing technology is not going to go away. There's some packaging that will be there in the world. Every package has to carry a label. So print inspection is something very important even in today's world. So this system looks for defects on plastic film that is used to package milk. So you see, these are the film that's running, and the system found this defect. There is something sticking here, right? And that's why it automatically stopped at such a high speed. And then this portion is cut and thrown away, so that it will not go into milk packaging. Because if by chance it goes into milk packaging, and if it shows up inside milk, then it's very bad. So, and unfortunately, plastic carries electrostatic charge, and it can attract insects and dust particles and so on. So it is necessary to inspect every area of this plastic film before it goes into pouch making machine. So this works at very high speed. So it's got a high resolution line scan camera that captures these images, and then every pixel, after a lot of algorithms like alignment and differencing and noise reduction and so on, it spots those areas where there is a possibility of a defect, and it removes it from the consideration. Okay, I think that's it. There's so many things, but we can stop here. If you have some questions, I can take.
Yes, sir. Very informative session. It was your conduct is the best example, I think, of why we have titled our FDP as a practical approach. So we have some questions here, sir.
Okay.
Shital is asking how the video frames are handled while real-time segmentation.
Okay. So I think that principle for something like this is always the same, that the implementation scheme or architecture has to be typically multi-threaded, and the aspect that interfaces with the camera so that no frame is missed, it has to implement some kind of a buffering scheme, and the processing thread actually is synchronized with this. It's picking up frames from the buffer and processing. And then you need a very stable or robust mechanism to synchronize these threads.
One more question is how much probability of false acceptance in the X-ray inspection of raw materials?
Yeah, again, it's a very interesting question. I think all these systems which are doing human job automatically, there is always a possibility that there is false rejection, right? In fact, even with humans, there is a possibility that there is false rejection. If a human is asked to look at potatoes whole day, and if he's looking at thousands of potatoes, probably at the end of the day, he'll start seeing everything right or everything wrong. So, and this can happen to a machine for technical reasons, that the light source has changed its intensity, or there is dust in the air and things like that. So false rejection rate of a system is always a very important parameter. So when we work on a vision system, we ask this question: what is the false rejection rate you are ready to accept? Because every rejection to the industry is a problem. They have to take that piece out, and it's a loss of production. It's a stoppage of their line and so on. So we had better have a very low false rejection rate. But ideally, you can't have zero. It will be maybe 1 in 1,000, 1 in 10,000, or something like that. And we have to work with that goal.
So next one question is what deep learning algorithm that best suits for filter optimization?
Actually, I'm really personally not so well versed with that, but my team tells me that there are various, for example, if the goal of filtering can be defined in terms of some sample outputs, so you have an input and a sample filtered output with that particular goal embedded in it, I believe you can actually train a convolutional neural network to capture that filtering aspect through its layered convolutions. So you can use any network. So it's really difficult to say one framework better than the other. I think in our company, and personally, I have played a little bit with Cafe CNN, and I found that quite interesting.
Yes. I think time is not permitting us to take more
Yeah,
questions.
so we can stop here.
Yes, sir.
So thank you very much once again. I really enjoyed being part of this event, and I'd like to wish you all the very best.
Thank you.
Thank you, sir. Thank you, Vishwas, sir.
You are most welcome. Yeah. Okay. Bye-bye.
Okay, bye.
Good morning, all. My name is Amruta Mohite. My greetings to all of you. I'm honored and lucky to have the opportunity to give a vote of thanks of today's first session of Signal Image Video Processing, a Practical Approach 2020. Today, my words are not enough to express the gratitude on behalf of ENTC Department of Government College of Engineering, Karat. I would like to thank today's speaker, Dr. Rudpika sir, who graced us with the thoughts provoking address set a perfect platform for college as well as our department. Thank you very much, sir, for your valuable guidance. Now, moving towards the second session of today's Signal Image and Video Processing, a Practical Approach 2020. It's my privilege and pleasure on behalf of ENTC Department of Government College of Engineering, Karat. I welcome you, all of you, today here. We are delighted to have Dr. Patwardkar ma'am here with us for this second session. I request ma'am to share knowledge in our signal image and video processing practical approach 2020. So, short introduction about Dr. Varsha Patwardkar ma'am. Dr. Varsha Patwardkar is Associated Professor working with Government College of Engineering, Aurangabad. She is having a 23 years teaching experience. She has completed PhD in biomedical image processing. She is a recognized PhD guide for Dr. B.M. University of Aurangabad. Signal and image processing is her area of interest as well as a research. She completed her research project for DRDO Pune. She is a member of ISTLM professional bodies. She worked as a reviewer for two international conferences. She organized 5 plus training. She had just 15 plus expert lectures in digital image
Hello.
processing, MATLAB, and outcome based education at
Hello.
many colleges. She had published 40 plus papers in the international, national journals and conferences. Thank you very much. I request ma'am to start her session.
Sarita ma'am. Hello.
Hello, am I audible?
Yeah,
Yes,
you are
ma'am.
audible.
Yes, you are
Okay.
audible.
I guess Karvankar is calling phone.
Yeah,
Let's
yeah.
not need.
Yeah. You are
It is okay?
audible. Is your camera okay or not?
Yes.
Switch
Camera
on
is
the
what?
camera for a few minutes. Switch on the camera, then share the screen and start your presentation. Then you can switch off your camera.
Okay. Is it okay? It's working now? Yes.
Yes,
Yeah,
yes.
camera. It's okay. Now share your presentation. Share your screen.
Yes. Yes. And now how will I have switch off my camera? Let me switch off first, and
Okay.
I'll share the screen. Yes. Is my presentation visible?
Yeah, it's visible now.
And
Run the
yeah,
show.
voice is yes. Is it
Yeah.
okay? Yeah. Shall we start the session?
Yeah, it's okay. Yeah, you can scroll down. Just one
Yes.
slide. Yeah, it's okay. Okay.
It's okay. You can see all those.
Oh, yeah, yeah. You can start the presentation.
Yes. Thank you so much, Anil sir, giving me the opportunity to discuss with the faculty in this particular FDP. Initially, let me confess, like I have two challenges. The first one is the participants, the audience is invisible. So we are not habituated to talk to the audience which are virtual. I mean, we generally have a feedback system looking at the faces of audience, what pace is to be maintained throughout the presentation. But let me try today with the virtual audience how it goes is the first challenge. And the second challenge is Dr. Upika sir has given a wonderful delivery and he has given a particular level to the topics he covered. So to maintain that particular level is also another challenge for me since he is associated since 89, he is associated with the industry work. So let's see how it goes. Let's begin with the sensation.
Sorry to disturb, but
Yeah.
so audio is not so clear. Do you
Audio
have
is
headset?
no. I am putting it on laptop. Is that not clear?
Voice is not coming clear.
Now is it okay? Hello?
Some background noises are coming.
Background noise. Not from me.
Headset. Okay, headset. Can
Headset.
you connect the headset?
Just hold on. Hello?
Yeah, yeah. You can speak now.
Audible now? The
Hello.
voice is clear?
Yeah. Yeah, you can start.
Yeah. I guess the earlier sentences few must have received, so I'll not repeat those. Let's begin with the session.
Yeah.
I being the core teacher, without touching a small theory part, I cannot directly jump on the applications. So I start with the digital image processing. Though the slide is indicating applications, we'll initially briefly go for a little theory part of the image processing, and then later the second half we'll cover with the applications case studies. So here we go. Now just look at the slides and just watch few slides I'm going to show here. First, second, third, fourth, fifth, sixth, and so on. So my question is, of course, I know I don't get your audio here, but you are looking the throughout the images, and your brain is doing something uh, with the images. For example, here you look at, say, you must have given a thought that it's a sorting problem or a segmentation problem. It's something which is a temple. It's something which we are hungry to, and then these so many things. So what do we do exactly looking at the images? You have been processing the images and extracting the meaningful information from them. What is so important about that is, I'll tell you, if I go for, if this is the image, say someone is interested in identifying how many people are there around the shore, someone is interested in having the level of the tide, someone is interested in looking at the monument. So the issue is, the challenge in image processing is, in a given image, some application says that it is object and the remaining is the background, whereas the other application says that the earlier object is now the background. If I am interested in counting the number of people, the rest of the things becomes the background. If someone is interested in looking at the tidal levels, we will consider people in the background. So the same image can be interpreted in different ways depending on what are the applications we are dealing with. So you have been processing the images and extracting the meaningful information from them. So what is this image processing? It is the manipulation of images to extract the information for a particular application. Oh, this is important slide for us because it tells us, as long as we are dealing with certain application, we need to choose the modality. By choosing the modality of the image, we are choosing the wavelength. For example, if we go to doctor and some fracture issue because of, say, accidental case, then we cannot have a visible spectrum as a wavelength. We cannot choose the ordinary camera to have a photograph and check where the bone crack is there. So we have to switch over to X-rays. Suppose the application is for galaxy, some happenings in the galaxy is to be noted. You have to switch over to the gamma rays. So the wavelength is to be, modality of image acquiring is also changed. So this is a very good. Everyone is familiar with this. This is from Gonzalez book, the Bible of image processing, I would say. And all the steps of image processing are known. I just go through the slide quickly without explaining too much because I have some images to show you the result of all this. First, whatever is the problem domain, the knowledge base, the database, everything, the complete umbrella is to be covered over here in the knowledge base, starting with the acquisition, then enhancement, then restoring probably, color image processing, high resolution manipulations, compression, morphology, segmentation, and two more steps till object recognition. Of course, all these steps are not essential for each and every application. Depending on the need, we have to choose which blocks we are working upon. Then these are the areas of image processing. Typically, we have, I'll show better through the slides only. The first one is image enhancement. This is the satellite imagery acquired. So this is the input, and this is after enhancement, how it looks like. So if you look at the original image, it is little washed out kind of thing, highly bright it is. So you can adjust the contrast and you can make it like this, so that is the image enhancement. And next is deblurring. Maybe because of some issues with the imaging modalities, there is a problem with this image, and you can correct it with a deblurring mechanism, and the clear picture is available over here. Then next is image depainting. Probably this is an older photo, and then because of storage, the albums are destroyed or some problem is created to the photos, you can have a depainting and have a clear picture of that. So that's a image depainting. This is typically we face when we scan some papers, we get the noise like this. So we want to get rid of the noise. We'll go for image denoising algorithm for that. And we get a clear output. The next is age detection. So this is the building out photograph, and the lines only are highlighted. Ages in the building photograph are only highlighted. A typical obvious application which I have conducted as an assignment in my master's class, that the wall is given to the students and they have to take the photograph and identify how many liters of paint will be required to paint this particular wall. Obviously, the calibration of number of pixel and the dimension of the wall has to be very proper so that the correct detection or prediction of the liters volume of paint is done by the students. The next is segmentation. Next is, we are very well familiar with this, the fingerprint matching. We generally do it every office, every college is having a biometric now. So we are knowing this. Image compression. Now we are striving for the bandwidth always, so it is better that we have a compressed image sent over so that the bandwidth will be effectively utilized. And there are so many applications like industrial inspection. Since yesterday, we are being discussing this industrial inspection. Today morning also, Udpikar sir has covered lot many industrial applications. Even surveillance and security applications also he has covered. The next application is face recognition, gesture recognition, space applications, medical image analysis, autonomous vehicle, virtual reality, and many more. You just name the field, there will be the application of image processing. In typical industry setup for computer vision system, you have the goods on the conveyor belt like this, and there is a illumination, and this is image acquisition. This is a camera typically, and then the camera signals are captured by local host and given to the central processing unit like this. The second application is, again, I'm talking about the industrial inspection and quality control. These are few examples. Here, this is a typical assembly line thing, and through the image, it is identified if some component is missing onto that. Here, that is a capsule, the tablet manufacturing unit, and if by mistake the tablet is not inserted and the paper is pressed onto that, it can be detected with the image processing only. This is the application indicating the level of medicine in the bottle, and this is how many air bubbles are there in a uniform plastic surface in the plastic industry. Then this is a document handling. Probably the archaeology department needs this a lot because the olden documents are to be preserved for a reference forever. Then next is signature verification. It's a digital era, so everyone is trying to switch over on secured digital transactions. So digital signature is important. Biometric. These are multimodal biometric. Just example I have given. Out of that, the fingerprint we are familiar with. Day to day we use it. Then fingerprint verification and identification. The first part of the slide says that who am I? So my biometric is given and my ID is recognized over here. Here in the second part of the slide, the biometric is given, name ID is also supplied, and I am who I say I am. And the machine tells really you are correct or you are not correct. Like the Aadhaar card verification everywhere. Then fingerprint identification, again, it's a biometric type. Object recognition, if you see a particular reference views and the object is determined, this is something that this is the object to be verified with the images given. So this particular two images are having that particular object is found out. Then Department of Defense, they are identifying whether the tanks of enemy are available in the vicinity or not. They can detect it through the imaging. Interpretation of aerial photograph that is already satellite imaging. Autonomous vehicles, land, underwater, space, everywhere. If you see the camera is substituted at this point, needed, and so that the image processing modules will be inside the microcomputer. This is for video processing. Traffic monitoring can be done very well with the help of image processing or video processing. This is face detection. I'm just skipping the slides and showing you what I just wanted to tell you how versatile the image processing and video processing things are. I mean, you can identify so many areas of applications of that. Then next is face recognition. Next is facial expression recognition. Next is you have hand gesture recognition, human activity recognition. Maybe this is essential to identify what is happening. Like the forensic will be more interested in such kind of applications. This is a well concerned area of everyone, of medical application. The screen cancer, breast cancer can be detected with the image processing. We'll be going through few examples later on. And image morphing also for some of the applications will be needed. Artificially inserting the object which is not there already, which is inserted with the help of image processing. And this is visual inspection. If you subtract the two, you identify that this object is missing, this IC is missing. This is expected. This is the standard image given, and this is the developed product. And out of that, if the comparison is done, this missing object will be identified immediately. Because in so much of densely populated ICs and components PCB, visual inspection is little bit difficult. So image processing helps in this area. So demodulation, if you see A, E, I, O, U is determined with the help of character recognition, optical character recognition. So this is just a basic theory what we have gone through, and we have just seen the umbrella of applications. So I guess it's a time for demo. I think every participant is dealing with teaching fraternity. I mean, every participant is faculty somewhere. So since so many days the pedagogy trainings are bombarded, and we understand that to break the monotony, you should have something with you. So I'm going for a demo here. Let me just open a MATLAB. Basic operations, image operations, a demo I'll be showing you. And then we'll resume the PowerPoint presentation to go for the case studies. Am I audible? Hello? Am I audible, Anil?
Hello? Hello, madam. Continue, please. You are audible.
Okay. So I'll be going for a demonstration now. This is a GUI created to indicate all the basic image processing operations. We'll go one by one all the buttons. Image negative. So here is the input image, and after this negative, yes?
Madam, screen is not visible.
Oh. So
Switch
what do
to
we
the
do?
MATLAB screen. Switch to MATLAB screen.
Yeah, here I am.
No, in the screen sharing applications.
Achha, screen sharing. So I have to go on.
Screen sharing, you have to switch between the two screens, PowerPoint and MATLAB.
Okay. So how do we do that?
MATLAB screen is not visible to participants.
Okay, okay. So where from I should try that? In share menu?
Yeah, in share menu.
Share my screen?
Share my screen, there might be a combo available. You can switch in between the two screens.
No. Share my screen is already done.
Yeah, here you can switch. You can close this browser window.
Close. This mailbox also. Now is it visible?
No,
MATLAB
close this browser window. No, close this browser window. Now MATLAB is visible.
Okay. Now I'll just run this application. Let's see what is visible now.
MATLAB. MATLAB.
Okay, GUI is visible?
Yes,
Yeah,
yes,
yeah,
yes,
yeah,
yes.
yeah.
Okay, I'll continue with this. Then again, maybe I'll have a problem switching back to the PowerPoint. Then help me out. Okay.
Okay,
Yeah, yeah, yeah,
okay.
Yeah. So negative button is visible. So if I press on negative button, the input image is this, and output image is a negative version of that. Then we have this has to be contrast stretching. So for contrast stretching, we need to give the input gray levels, say 50 to 100. I have given this is a contrast stretched image. Input image is same, the cameraman. Then we have say bit plane slicing. So there are, it's a 8-bit representation. So we have the 8 bits over here. Then histogram, this is the image and the histogram is displayed over here. For histogram equalization, we have chosen the different images. Typically, the standard images from MATLAB library are chosen for these applications. Then we go for the averaging. In averaging, it is asking us to enter the mask size. So I have given 3. It gives me the average over here. Then we go for median filtering. Yes, because of median filtering, we know that the salt and pepper noise is removed. So if you see in the input image, the salt and pepper noise is there, which is removed after median filtering. Then the private, through the private, you can have the age detection. Here in the downside menu, bottom side menu, we are going to see the age detection again. Let me go for filtering. Again, it is asking me the mask size. Let me say 5 over here, low pass filtering. So it is blurring the image to a full extent because I have chosen the higher mask size. We go for high pass filtering. Maybe the mask size I'll give as a 3. And it is highlighting the edges in the image. This is the high pass filtering. Then we go for morphology operation study. So this is the original image is at the top side and the effect output image is at the bottom side. Erosion, obviously the characters are eroded. And dilation, yes, the dilation, this structuring element is of larger size. So everything is vanished out and we are having a white band only. Then opening, we know opening is, erosion first and then dilation. So we observe the output like this. Closing, the reverse operation of that. So we find this one. Now we go for point detection. So for point detection, let me pass the image to that. Just hold on for a while so that I can pass the input image from this directory. So this is Volkswagen logo I have chosen, and point detection is that is converted to dots. I mean, however number of points are there, it is showing us. Then we go for line detection. If I enter here 1, it will do one operation. All horizontal lines will be detected. If I do it again and press 2, it will be going for a vertical line detection. If I do it again here and press 3, it will go for all diagonal lines chosen. This is how the demo is arranged. Then we go for average thresholding. Then we go for low thresholding, low threshold value, and we go for high threshold value. If the threshold is high, everything is washed out. I mean, everything is darkened. Low threshold value, everything is bright. And average, okay, it has improved the quality a little bit. So this particular demo is arranged just to have a tour to all basic operations in image processing. So let us go back to the PowerPoint presentation again. Now coordinators will help me telling how to go for PowerPoint presentation again. I am on share this thing.
Just minimize now MATLAB window.
Okay. Yes.
Minimize again. Now your presentation is available. Just run it.
Yeah. Okay. I do it from. Now we go for image processing case studies. I have say 6 case studies. Let's see how the time cooperates. We'll cover as many as possible. So the first application is script identification using image processing techniques. Basically, a country like India, we are multilingual, lingual, and multi scripts are also available. So we have given a thought that we have some document sorting facility, so that the document is given to the machine and it will tell us in which bin it has to go. So we tried for this, and three different types of scripts were handled in the beginning. One is Telugu, the other is Marathi. Marathi is Devanagari, and the third is English. We tried it on three different scripts only. So as a sample paper is given, of course, we have chosen for typed document, not handwritten documents. So this is indication of Telugu, how it looks, and this is Devanagari Marathi, and English we are familiar with. Then to identify that every script has got certain features depending on how the horizontal lines, vertical lines, curves, downward and upward curves are used, different scripts are created. So the characteristic feature of Telugu script is there are tick-shaped structure on top of their characters. So we decided that Telugu script will be discriminated based on that tick-shaped structures in the document. Whereas in Devanagari script, we know that we call it as a Shirorekha. There is a horizontal line on each alphabet, each word we give in Devanagari, we give in Marathi. Script is Devanagari, I should say Devanagari only instead of calling it as a Marathi. So we have decided that for Devanagari script identification, let us try to check only the horizontal lines. We have thresholded it first. Of course, some pre-processing slides I am not including over here. We have decided that in this Devanagari script in Marathi language, there can be a minimum single character word also. So we have chosen the minimum number of pixels connected to be 2, and maximum for our document we have chosen it to be 8. Of course, it is empirically chosen and by observation chosen, and we have calculated, we have obtained horizontal lines like this. All the Shirorekhas are identified like this. Then after this step, we have computed the black pixels. We have done the same thing on English and Telugu script also, and I am sharing the result table for that. So for Devanagari, we are having, this is a single line and half line. So you are getting some numbers over here in Devanagari, whereas in Telugu and English, there are no numbers, I mean 0 numbers, because we have given a particular threshold. Above that threshold, if it contributes, if number of black pixels contribute, then only those are considered, otherwise they are considered as a 0 below threshold. So if the entire complete image is considered, these are the count available. Of course, these are 0 because of the thresholding added in the program. Then next, to identify the Telugu script, we have considered the tick-shaped object like this. Many characters in the Telugu script are having this tick shapes on the top of the character. So we have decided that just in the neighborhood, if you have the black pixel like this, and then after that in the upward direction, if you have the black pixel like that, it is to be considered as a tick. And we have added the algorithm and we obtained the result like this. So all ticks were over here. Whereas in the English and Devanagari, so many ticks were not available. In Devanagari, we do use matras, but then the frequency of appearance of matras is not that much, which is at par with the Telugu script. So based on this, we have decided, we have calculated this tick detection algorithm, a result I am showing over here. And in Telugu only we are getting the values, where other values are 0. Of course, here also we have put a threshold. Below that, if the value is, we are calling it as a 0 value. So then next is, this is just what we have done for this flowchart for Devanagari, Telugu and English script. First, the image is converted to gray, then have a thresholding. After that, horizontal line is detected, count it, then it may be a Devanagari script. If no, push it further for the next classification. Tick-shaped objects are to be determined. If you are finding more number of tick-shaped objects, then call it as a Telugu script. Otherwise, the next one is the English. The simple algorithm is used to sort out for 3 different documents based on the scripts used. The next, this is one area, one case study I have shared with you. The second is a little research-oriented. This one is estimation of hemoglobin using color analysis and neural network approach. So HB is a matter to worry, at least in Indian population, that to rural population is HB, the challenge, typically Adivasi areas and all, one has to bother about their health much because there is no medical facility available. But then this particular thing is estimation of HB through blood images. We tried. This is still going on. Everyone knows that blood consists of cellular material which comprises of 99% of RBC, and hemoglobin constitutes 33% of RBC. So with the help of blood color, we can find out the hemoglobin. So what we have chosen is a local hospital has cooperated us giving the blood images. They have given us 1024 by 1280 pixel resolution as per their microscope and camera cooperated. So we have converted all these given images into 256 by 256 standard small blocks. And then we have done, this is the block diagram I would share. Here is the some pre-processing after microscopic images, and then feature extraction, and then classification using neural network and calculating the correct classification rate. So for feature extraction, we have tried for statistical methods, we have tried for DCT-based method, and we have tried for binary feature extraction. Few I will share over here. And for classification, we have used a neural network. This is very standard one. Backpropagation neural network is used. So let me skip that. In statistical feature extraction, we have used the mean and standard deviation only. But while doing this, we have chosen the color model RGB and YIQ both. We have gone for a model RGB. Out of that, R plane only is considered, and YIQ, Y plane is only is considered for estimation of this hemoglobin. We have tried two different techniques over here. One is estimating the hemoglobin value directly, and the other is a classifier. I mean, we have been supplied with the doctors that if the HB is above this, we call it as a normal. If HB value is below that threshold, we call it as an anemic. So we have two classes, either normal or anemic. So whenever we are dealing with the classifier, it is normal and anemic. And the regression based method, we try to exactly estimate the HB through the images. Let me share the next one. This is a DCT extraction. This block is only changed. Rest all is common. So these are the values available. And out of this observation, this is epochs versus accuracy. Epochs on x-axis and accuracy on y-axis. So Y plane gives a better result for this. This is a two-class classification. I mean, the subject is normal or subject is anemic. So Y plane has cooperated nicely. And the second one for detection, for declaration of HB value, we have gone for regression, and we have used eView software for this. It is available online, and we tried through this eView software. Linear and multiple regression. So we have chosen this multiple regression because we had this RGB component of the image with us. So we have gone for this multiple regression analysis. Here we have converted, there are two things we have studied. One is without D. This D coefficient is not considered, only RGB three values are considered, and the estimation is calculated given. And with the four, I mean, if you look at the slide, 3 regressors and 4 regressors, we have done this. These are through RGB. These are the actual values given by the doctors to us. The patient is having 13.9 as a hemoglobin, and 3 regressor has predicted. This is through our calculations. I mean, this is through our regression model, 12.81, and 4 regression model has given 14. So if you look at this last two columns are indicating us how much is the error in actual value and the algorithm result value. So if you look at this, 4 regressor gives better results. Then the next one, the same thing, the 3 regressor and 4 regressor thing is tried on YIQ feature set also. And here also this HB value, the first column is indicating the values given by the hospitals, and the values obtained by 3 regressor model and 4 regressor model are like this. So if you average out the error, of course there is an error, but then I told you initially that the work is still going on. We have to go for more accuracy to declare that we are at par with the medical values. So better that we go for classifier, which tells us whether anemic or not anemic. If anemic, then doctors have a call what to treat. If normal, then you don't have to do anything. So this was my second case study. I think I am audible and the slides are also visible. Hello? Am I audible? Hello?
Yes, ma'am. Yes, ma'am. You are audible. Yes.
Yeah, okay. So I'm going for the next case study, that is plant identification using leaf images. So simple steps we have used is image acquisition, image preprocessing, feature extraction, and plant identification. We have implemented 3 different types of feature extraction techniques. Parameter measurement is simple one, chain code and Fourier descriptors is standard. So I can go through that. We have used 2 different databases. One is we have prepared in our college campus, we have a lot of trees. So we have collected leaves from the trees and we have scanned and then the database is created, and one which is available online. Mr. Wagmare has shared it online. So we have taken up that also so that we can validate the results on both the data sets. The next one is geometric parameters, the length of the leaf, width of the leaf, diameter, leaf area, leaf perimeter. All these were calculated based on the, first we have had a boundary extraction, and then based on the boundary extraction, we have calculated all these dimensions. And basic features are aspect ratio, form factor, rectangularity, narrow factor, perimeter, and length and width. So we have had a combination of all the measured things. And based on that, some features are derived also. So number of white pixels and the area of the leaf. And we tried using concatenating all these features in a feature vector. And we have obtained the accuracy for database 1 to be 81.25%. And for database 2, it is 85 or 90%, depending on what is the training set was chosen. Second technique which was implemented was the chain codes. We are well versed with the chain code. We can use 4 direction, we can use 8 direction, and accordingly the chain codes can be generated. So on the leaf boundary, we have tried on this chain code, and based on the chain code obtained, the bending energy is very good discriminating feature we have obtained. And it's a big list of features what you can calculate out of this. You can go for kurtosis, skewness, typical statistical, and the bending energy combinations also you can have. So that depending on the concatenation of these features, the accuracies, different accuracies are available. I just share with you later on the comparison result. The third technique used is Fourier descriptor. So this is the boundary of the leaf, and boundary points are identified to be x1, y1, x2, y2, and so on. And each point is considered as s of k is equal to x plus iy. And then this is input to the Fourier transform. And based on that, the features were obtained. Typical features were maximum value of absolute value, minimum absolute value, and average absolute value. Imaginary part we have not considered over here. Only the absolute values were considered. And this is the comparison of all 3 methods. We have tried on 2 class classification, class 1, class 2, class 1, class 3, class 1, class 4. All combinations we have tried, and 3 different methods were used. So here the average, here the average accuracy is available. For method 1, we are getting 96.66, for method 2, 93.66, and method 3 is giving us 83.33. This is only for 2 class classification. If we increase the number of classes, then the accuracy probably decreases a little bit. So this is for plant classification based on the leaves. The next case study is population estimation of whitefly for cotton plant using image processing approach. Basically, we are the country more relying on the farming, and we know what the problems farmers are facing. So we took a call that we should help them out to identify the presence of pest, and depending on that, how much is the pesticide to be given to the plant. So we tried, that's an endeavor just to help them out. So this is a typical white fly on the leaf. This is a single, there are many and there are many. So what happens is, because of anxiety, even farmers use more pesticides than necessary sometimes. And sometimes it also happens that they neglect 1 or 2 pests, and then the crop goes down because the reproduction rate of pest is too high. One has to monitor every day, and accordingly the pesticide quantity is to be adjusted. So we have just done the endeavor. We have just had an attempt to count the number of pastes on the leaf. So I'll show you the algorithm what we have used for that. The problems identified was overuse use of the pesticide, reduced crop quality and yield, and high economic losses. What do we need to do is control the pesticide use and identify the number of pests available on a given day. So the algorithm used was acquiring the image, then color space conversion. Here we have used HSV conversion, HSV model, then background subtraction, thresholding, and morphology. I'll show you actually one by one. So the first step is color space. RGB is converted to HSV and HSV image looks like this. This conversion of color space is just to find out a mask to separate pastes from the background. So HSV gives a good color perception. So we have considered RGB to HSV conversion. And after that, this HSV is divided into three planes: hue, plane, saturation, and value. And for these three planes, a threshold is defined based on the histogram. And after that thresholding, a mask is obtained. So mask looks like this. Excuse me. So this is how the mask look like. And this mask is then overlapped on the original image, where this is black, that is supposed to be the background in the original image, where this is white is supposed to be the presence of paste in the original image. So we have used this only the mask so that we can use it on the original RGB image. So after applying the mask to the original RGB image, we have done an adaptive thresholding. So what is done is initially threshold T1 is calculated, mean value, and we have had two different groups, then G1 and G2. Below the threshold value and above the threshold value. Then these two groups, we have found out M1 and M2. This is typical adaptive thresholding mechanism. And then again, the next threshold is calculated based on the means of the two. And this is repeated for some time. And finally, we obtain that adaptive thresholded image like this. So what is the problem associated with the thresholded image is if you look at the image, there are certain dots or there are certain connections like this. So obviously it is a call to remove this noise. So we have done a morphology based operation, removing the noise for removing the noise from the image. This operation separates the overlapping pastes and removes all the object containing fewer than the given number of pixels. So we have set here 10 pixels. If the object is having less than 10 pixels like this, that is to be removed. So we have done that. And then after that, we have had a counting of all the pastes. So these are the bounding boxes which are giving us the number of pastes available over here. So in this particular figure, we have 199 pastes available. This is the algorithm declared number of pastes. This is manually counted number of pastes. So we have an error column over here like this. So again, it is a demo time, as the pedagogy says that you should go for a break. Again, I need to switch over to MATLAB. Maybe the coordinators again have to play a role in helping me out how to go for MATLAB.
Your MATLAB window is now visible to us.
Yes.
You can take even a water break.
You said something?
No, you can take a water break also.
Yes. Okay, by the time I will check
your
my
MATLAB
folder.
window is now visible.
Yes. Let me have a break of 1 minute so that I can have the next folder loaded onto my MATLAB.
Okay.
Start? Hello?
Yes, ma'am.
Hello.
Yes, ma'am.
Switch
Simulink
on
model
your
is.
mic.
Oh, it's on.
Yeah, yeah. Now we are here.
You are audible.
Simulink
Yes.
model is visible or not? I am asking.
Yes. Yes.
Yes, yes, yes.
Then okay. I can run that. For that, I'll have to enter the image here. I'm just entering the input image. I'll show this on one or two different images. I'll run this Simulink model. Okay. So I'll minimize this and I'll show you one by one sequentially so we'll understand how the algorithm is implemented through Simulink. So here video viewers are added as a block so we can see one by one. This is what is the input image. So let us count the paste manually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 pastes are there. The next is this is the normalized image, HSV image, color thresholded image, and then noise removed image like this. And the algorithm here goes wrong, telling us 17. So there is an error of 2 pastes. Manually we measured it is 15, we calculated it's 15. Now it is giving us 17. I'll show you one more image over here. Okay, we'll apply that change and then again I'll have to run the model. So I can show you the images sequentially. The first one is the input image. Looks like this, having 6 pastes. The second looks like normalized image and converted to HSV. So we have this HSV representation. Here we have color thresholded image and this after the noise removal. So this is also giving us 6. So for this image, it works well. 6 pastes were there if you see the original image. And the count is also at the end, if you see the display, it gives us how many number of pastes are there. So with little error, the Simulink model also works fine. So with this, I will go back to our presentation. Let me minimize all these slides given by MATLAB. Is my presentation available now?
Yes. Yes. Yes.
Yes, yes.
Presentation is
Okay.
available.
So we continue with this next case study. It is the texture analysis of CT scan images. So there were so many imaging modalities as far as biomedical imaging is considered: PET, MRI, X-ray, CT, thermograms, and so many. So we have chosen the CT scan based images. This is a sample of CT scan images of human body. Organ-wise segmented images. This is bladder, this is liver, this is spleen. These are the right and left kidneys. This is just a sample image I am showing. The first step is we have to create the organ image library. So CT scan is the imaging modality chosen. And then in CT scan, you have 4 different modes where the patient position is to be adjusted so as to collect the data. You can have a brain CT or HR CT or abdominal or lower abdominal covering pelvis also. So for getting brain and neck images, the first one is used. For lung CT, the HR CT is used. I have worked on, we have worked on abdominal CT scan and the lower, that is bladder and kidney CT scans also. And we have created a biomedical image data set over here, BOID we are calling it as. Then there are so many methods implemented. I'll try to cover 1 or 2 only. So methods of texture analysis, typically we can go for statistical or structural or signal processing. So I'll cover this statistical method used in this project. It is statistical is first order, second order. So second order is based on co-occurrence matrix. So we have gone for co-occurrence matrix. So this is the basic theory of co-occurrence matrix. The crux of co-occurrence matrix tells us the probability of co-occurrence of the same image intensity within a given distance, within a given angle in the image. So this is very basic co-occurrence matrix theory. So let me skip the slide. And what I have done is bit plane slicing and co-occurrence matrices are combined together, and this is the methodology implemented. This is a data set. The region of interest is covered, is obtained, and based on that, 8 bit planes are separated. With this bit plane sizing, we know that each image, if it is represented by 8 bits, you can separate the image in 8 planes like this. So I have done it separation of the images in 8 planes. And then we have tried for combination of these planes, 1 and 2 plane together, 3 and 4 plane together, 1 and 3 plane together. We have tried for so many combinations. And the combined version of bit planes, we have applied the co-occurrence matrix. And based on that, standard 4 features were extracted and given to the classification. So I just show a few slides of the results. This is the combination of the planes. Bit plane 2 and 3 is combined here. 3 and 4 is combined. 3 different bit planes are combined here. 2, 3, 4, 3, 4, 5. We tried for many combinations like this. And onto that, the co-occurrence matrix is applied. And we have considered the features are given to linear discriminant classifier, and the percentage correctness of this brain and bladder images 90.85. These are the typical values, 99, 94. So it gives us good result when you have a combination of bit planes, and then to the combined bit planes, application of co-occurrence matrix gives us a good result. This is typical, the crux of all these bit plane slice and co-occurrence matrix combination method is explained by sensitivity, specificity, precision, and accuracy. So if you look at the last column, accuracy is very good. I mean, liver, 88% accuracy, it is correctly detected. Brain, 92% accuracy, correctly detected. And so on. Bladder, 95%, kidney, 90%, spleen, 84%. This is the accuracy of detecting these organs. And the next statistical method only, we tried it based on the local histogram. Actually, in the histogram method, we have tried so many. So I'll be sharing only LBP over here. That too, a local binary pattern, you have to consider you have to consider a central pixel, and with respect to the central pixel, the neighborhood, 8 neighborhood pixels are compared with that, and accordingly, if they are having a small value, considered it as 0. If they are having equal or greater value than the central pixel, they are considered to be 1. So you get all the 8 neighborhood pixels now represented by zeros and ones only. So to those zeros and 1, considering one particular sequence and multiplying it 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 7, so on, you get a number that is to be converted to decimal number again, and the central pixel is replaced by that number. This is what we call it as a local binary pattern. So through this local LBP concept, we have tried for classification and the classes 2 class, 3 class, 4 class, 5 class classification. Accuracy is directly represented over here. So 2 class, it gives very good results. For brain and bladder, it gives 98% results. And then as the number of classes are increased, then there is a decrease in the accuracy. The other method tried was a contrast. Now, how the contrast is obtained, you just have the image, have the mean of the image, and then subtract mean from all the pixels. So you get a positive and negative numbers in the image matrix, and that is considered to be the contrast. And based on the contrast, we have identified some features, and that gives better accuracy as compared to LBP. And this is again a crux of the LBP total sensitivity, specificity, precision, and accuracy. But as compared to the first method, first statistical method, that is co-occurrence matrix and bit plane slicing method combination, this gives a little less accuracy. There we have obtained the accuracy in 90s. Here we are obtaining the accuracy in 80s and 70s. Then the next is, as you remember, we have considered that texture analysis is carried out by 3 methods. Either you go for statistics, or you go for structural, or you go for transform. So transform based method, we tried for Gabor, we tried for wavelet and ridgelet also. I'll be sharing only few slides over here. This is a Gabor based result, Gabor based algorithm we used. Bank of Gabor filters is giving me n different images. Then non-linear transformation is applied to that, and then feature extraction. Typical Gabber, of course, scale is 3, orientation is 8. This is through the literature review we have decided these parameters. How do we identify this lower cutoff frequency, upper cutoff frequency? Maybe the question in the mind. So generally we follow what the literature says, and we have done that. So that is also giving us very good accuracy for 2-class classification, 90, 99, 93. Again, the classes are the different types of organs which we have considered. Hello? Someone is saying no audio. Am I audible?
Yes, yes, ma'am. You are audible.
Okay, some window popped up. You are not audible.
Yes, they.
Maybe somewhere some bandwidth issue or somewhere some internet issue will be there.
Yes, yes, yes. On their side, the problem is there, I think. Yes.
Okay, so shall we continue?
Yes, yes. We can continue.
Yes.
Yes.
Yeah. Okay, so Gabor-based method gives us the accuracy around in 90s. Next one, we tried for wavelets also. It is just a 3-level decomposition wavelet, giving us 10 different features, 10 different bands and 10 different features. We have used only the average of the band available as a feature, and the accuracy is as per the displayed 84, 84, 80 and 80. These are the correct detection rates. Then we tried the other algorithm also, that the CT scan image is given, and how to segment a particular organ. That algorithm now I'll be sharing with you. I mean, I'll be showing the slide for that. Earlier we have seen how to have a classification. Here the main image is given, and after that main image, automatically the liver is separated out. So we have the size of abdominal CT scan 512. The slice thickness is 10 mm. It is the specification of a CT scan machine used in the local hospital. And we have done the work based on the clustering method over here. Fuzzy C means clustering is used. I'll show you this one. The original image, then the wavelet decomposition. Through the wavelet decomposition, we have obtained the feature image, and based on the feature image, fuzzy C clustering mechanism is implemented, and segmented image I'll show you. So these are the stepwise results. And this is unsupervised segmentation, of course. So this is the image, and finally this one is separated out. This one is also separated. This is a liver, if you look into the image. And this is also separated. This is actually it is a cavity in the abdomen, and this is a cavity between the ribs and the organs. So all these cavity parts are detected by the algorithms. So then further we have to work so that we can separate out the liver. So this is unsupervised segmentation. So on its own, based on the feature values, the machine is clustering and finding out the organs. This is the technique we have used. The second one is a supervised segmentation. What did we do in supervised segmentation is we have considered 32 by 32 segments, 32 by 32 non-overlapping segments of this total image, and we have found out the features based on wavelet. And wherever those wavelet feature value matches, only those pixels are taken out, and that is like this. So this is a liver, and this is what we have obtained by supervised segmentation. So this is for segmentation of a particular organ. This is one another at this the first case study of biomedical image is over. The second case study is syndrome identification. The work is still going on. Syndrome identification based on the facial features or face images we have tried. A simple model is worked out here, and that is giving us very good result, and we have had a good publication based on that also. So the facial features I will be sharing with you. The facial feature points are identified. We tried with Viola Jones also. That's a standard algorithm everyone use, and locating the points is automatic in Viola Jones, and we have tried on manual detection also. So one year 4 points were detected manually. The other year 4 points. Around the lip and mouth 5 points, and so on. So total 25 feature points were detected, were identified, and based on the measurements, geometric features were extracted. So what all measurements we have done? We have considered the horizontal distances, eye to eye distance, ear to ear distance, then total leap coverage distance, and so many measurements. If you see in the figure, different parameters are measured. These are linear measurements. So and the issue is, even if the images were captured, syndrome identified as children's school is there in the Aurangabad city. So we have had a permission of the school, and we have gone to acquiring the images of those kids. The typical age group we covered is 8 to 15 years. They come to the school, and then in the school we have created a control environment and had the images. But still, because of the camera issues, because of there are certain artifacts, we need to have a normalization. So we have had a normalization by dividing it with this. If you see the distance from A to A dash, the complete horizontal line is in the denominator. Whatever we have the distances divided by AA, that gives us a good normalization. So with this, I'll directly share with you what is the accuracy we have obtained. We have tried here two different classifiers, linear discriminant and quadratic discriminant classifier, and training data set percentage